All right. So in the next section, we're going to take a look at predicates and quantifiers. All right. So a predicate is a statement that contains a free variable. All right. So if we think of x is less than 3. All right. And then we're going to, right, using quantifiers, we're going to test the validity of these statements. All right. So for example, what I mean by a quantifier, there are two of them that we're going to be working with. One of them is called the universal quantifier. Written like this, right? And this is read as for all. And then we also have the existential quantifier. And we have this, right? And this is there exists. Okay. So both are classifying different things, right? We say for all, so usually in conjunction with our variable, right? So for all x, or there exists an x, right? Now in terms of how that fits in with our statements, we could say, all right, let's say the statement is every number is even or odd. Okay, so let's say here now, let's make it as a predicate. We have x is a number. All right, and we could say E is the event that a number is even, right? So here, this statement here states that x is even. And then O, x, say that x is odd. All right, so now we could say here, right, now just put it simply, right, for a number, it is either has a choice to be, or there are two options for any number, right? It's either odd or it's even. It can't be both, hence the use of the or statement, right? X odd or x even, right? One of those is going to be true. Now, in terms of our quantifiers, the way we would write that using a quantifier, we would say something like for all x, ox or e to the x. All right, so we would say something like this. Okay, and again, the way we read that is for all x, O of x, x is odd, or e of x, x is even. Okay, now keep in mind here just a couple things here, right? This does not mean the same as this. All right, so that means a completely different thing, right? So again, we got to be careful in our language. Here what we're saying is for all numbers x, x is odd, or for all numbers x, x is even. All right, so either all the numbers are odd or the numbers are even, which is not what we want to say. All right, so just keep in mind here that how we write this is very important. And also one other thing is something called the domain of discourse. And again, where does x come from, right? From what set does it come from? Right, now usually here, right, well, not every number is odd or even, right? That's a distinction held to integers, right? And in general, in our discrete math course, our domain of discourse, unless stated otherwise, we can assume that it is the natural numbers. Right, so these are what we're going to define the natural numbers, right? The counting numbers here starting at 1. And so that is going to be important. So our goal here is we're going to begin here by wanting to, or start off trying to translate statements from informal into logic, right? And that is going to come in the form of two types of statements, right? One is going to be for all x, p of x implies q of x. All right. So for a particular value of x, it's a p thing, right? It belongs to the statement of p, and that is going to imply q. The other one is this: there exists the existence of p of x or q of x. All right. Okay. So usually the type of statements that we'll be translating are informal language into logic here. Let's take a look at an example here. All right, so let's say that the statement is every student in this class has studied calculus. All right. The first step is to try to rewrite this now in our way that we can use predicates, your logical connectives, quantifiers, right? So we're going to need to introduce some variable, right? So you could say here, right, for every student x in this class, x has studied calculus. All right. So again, x is a student, and we'll call the event c of x here, that x has studied calculus. Okay. All right, so now in terms of putting this using our quantifiers, so every student. So here, this would look like for all x, c of x. Right, that would be the equivalent statement in our logic language. Okay, now here we kind of assume that the domain of discourse was just the students in our class. Right, but what if we wanted to expand that domain of discourse to be every student at our college, right? So we can expand here by saying for every person x, if person x is in this class, then x has studied calculus. All right, so again, x is our variable, it's just a person. And here we can think of, so kind of expand our domain of discourse. X is a person or student, we'll just say a student at Chabot. Chabot College. So now we've changed our domain of discourse, right? Okay. And then here we'll say the statement S of x is a person x in this class. All right, and now we could say that for all x, s of x, person in this class, again, that implies something, right? This is true, then this implies a conclusion, which is has studied calculus. All right, and that is how we would write something using our propositional logic here. Okay, now again, be careful, right? Why is it this as opposed to something like this? Right, what is the difference? What is this telling me here? So now this is saying for all x, right? So here, now this is saying all of x. So this is all students at Chabot College. If that were the case, all students are either, they are not either, all students are in this class and have studied calculus, right? Which you know to be false. Okay, so again, just keep in mind, order which logical connective is going to be very important. We have to be very rigorous in our language.